this is another like measure of estimation variance, of precision of our estimate. Instead of reporting one number, our estimate is 0.23, we can report an interval, and the interval somehow encompasses our confidence, and what this means precisely is that we think that the interval has been constructed in such a way that if we repeat this procedure in X% of the cases, it contains the true value. And the typical values are something like 95%, 90%, or 99% confidence intervals. Those would be the three that are used more frequently. And so the idea, it's not formally correct, but you can think as sort of like this interval covering the true value with a 95% probability. Yes. So here the idea is we're going, and you see how we construct it is just we take as the midpoint our coefficient, our estimated coefficient, and we add the critical value times the standard error. Yes, and we subtract it. So this is how we do our interval around the beta 1 hat. So here again, the question is a little bit, okay, where do we take this number from? Where do we take the standard error from? And the default would be the default OLS standard errors, but we can also use the statistically consistent standard errors. And these questions, this question here asks us to redo the first exercise, but instead of using the p-values to test, that we just compute the confidence interval and see whether the confidence interval covers the true parameter. Yeah, so whether the true parameter lies within our confidence interval that we have computed. And this is again a way of testing. Yeah, you can if the confidence interval, if your hypothesized value is in the confidence interval, you fail to reject. If it's outside, you reject. Okay, so now let's have a look at the script that accomplishes this. So this is the last part. The setting here is exactly the same as in the first exercise. And now here is where we're going to save our results. Yeah. We're calling this incl in the sense that this interval includes the true value. In this case, it's a 1, and it's 0 otherwise. So if the interval does not include the true value, then it's then we record a 0. So this is all exactly the same as before, and the only difference starts here when we construct the confidence interval. So you see, we extract the standard errors. We can take the standard errors again from this coef test, yeah, and so we store them in, or we call them SE-OLS for the OLS standard errors, and now we produce the lower and the upper bound of the confidence interval. The lower bound is going to be the coefficient, yeah, the estimated coefficient, minus critical values times the standard error. Yeah, the standard error we have defined here. Where have we defined the critical value? Here. Yeah, so we're taking here the critical value. Critical value is just a number, so this doesn't change over simulations, because this is a quantile from the t-distribution. Could also have taken a quantile from the normal distribution. Yeah, so but here, since we're working with relatively small sample sizes, 50, 100, the t-distribution will work better. in cases where we have a scholastic variance, this will be exactly the right distribution. But you know that as n becomes larger, this is going to be very similar to a normal distribution. And so because this is a two-sided test, we are looking for the 97.5 quantile. Yeah, so we want to know what is the value where we have 2.5% of observations or of the t-distributions are further away, and 2.5% are smaller than this, than minus that value, because it's symmetric. And the way that we ask this of R is just this, yeah, quantile the t-distribution. We want the 97.5 because that's half of 5%, yes, leaving 2.5% at the very tail. And the degrees of freedom are n, so the sample size minus 3, because we're estimating 3 parameters, beta 0, beta 1, and beta 2. Good. So this is this number, which is approximately 2, yeah, is as n becomes larger, this is going to go towards 1.96, so it's about 2. We write it here, and here we have the, here we have the Euler standard errors. And then here we look at whether the actual estimate, the estimate lies inside or outside these bands. You see, we have here, this is going to be 1 when beta is both larger than the lower bound and smaller than the upper bound. Yeah, so in this case it's included, and we write a 1 into our results. Otherwise, it's going to write the 0. This does exactly the same thing with the heteroscedasticity consistent standard errors. Yeah, so this, we can run this, and then we will get as output this table. Let me show you the table. Yeah, so we get this here. So these results, as it says here, are the proportion of the, these are the proportion of the 1,000 replications in which the confidence intervals includes the true value of the 1, which is 0 in this case. And the same way as we call the other thing that we were looking at frequencies, we call these things coverage probabilities. Yeah? The probability that we're covering the true value. And because we're testing at the 5% level, we should be covering the true value in about 95% of the case. In this case, we would have this correspondence of nominal size and actual size. And if you look at this, and if you actually run it with the same random seed, you will see that you get just 1 minus the previous results. Yeah, because this is exactly, it's mechanically the same. You can test either with p-values, or you can test with confidence intervals, or you can test by comparing the t-statistic to a critical value. These are all exactly the same. It gives the same procedure, just that here we're looking, instead of looking at the 5%, we're looking at 1 minus that, so we're looking at hopefully 95%. Yeah, and so we see again in the case of heteroscedasticity in the DGPs 2 and 4, matching to the size which is too large, we see that the coverage probabilities are too small. Yeah, so the confidence interval that OLS is giving us is misleadingly optimistic about the precision of the estimates. And the message here is exactly the same. Better to use the heteroscedasticity consistent standard errors. All right. This is all that was required in this week's tutorials. Do you have any questions about this last exercise with the confidence intervals? All right, if that's not the case, I think this is a historic moment because it's the first time that I'm actually finishing this tutorial on time. Don't forget to submit your assignments. The deadline is tonight, so please do that. And yeah, if you don't have any questions, then feel free to go and enjoy the rest of